This is section 6.2, day 2, and we're continuing this to kind of solidify the strategy for doing U sub integration. So we're going to continue along this path with this 8-step process, and we're going to look at this first example here. So we're going to go through those steps. The first step is to identify an expression to factor out, and so we want to look at that relationship between function and its derivative. So we're going to identify the expression to remove, and that's that function expression right here. So when we do that, when we try to identify that, we look for grouping symbols. In this case, the grouping symbol is the square root sign. So we're going to remove the 1 plus x squared. Step 2, we're going to set it equal to u. So u equals 1 plus x squared. Step 3, we're going to differentiate. So du dx equals 2x. And then step 4, we're going to rearrange this and solve for dx. So that means multiplying both sides by dx, and that means dividing then by 2x, excuse us. So here's our dx solution. So with our this and this, we can then rearrange this. So when we substitute, we keep the integration sign, and piece by piece we have to decide what comes out and what stays. So the 2x stays, the fraction bar stays, and the radical stays. And then the 1 plus x comes out, and we replace it with a u. And then the dx comes out, and we replace it with a du over 2x. And if we've done the substitution correctly, and we know we have this relationship between function and seeing the derivative there, then we should see that that will end up canceling every time. So this easier integration expression becomes 1 over the square root of u du. Or, making it even simpler, instead of 1 over the square root of u, we'll call that u to the negative 1/2. So we end up with a simpler integral to take an antiderivative of, which looks much simpler than this. So now we've got something that's a simple power rule. So we bump up this power by 1 to u to the 1/2. That's step 6. And we divide by that new power 1/2. Now dividing by 1/2 is the same as multiplying by its reciprocal, which is 2. So this ends up being 2u to the 1/2 power. Step 7 and 8 is our combination here. We replace the u, and we put a plus c on there. So the u is really, we get this back in terms of x, which is 1 plus x squared, so it's 2 times 1 plus x squared to the 1/2 power plus c. The other way you might see this is 2 times the square root of 1 plus x squared times c, or plus c, excuse me. So let's take a look at example 6. So example 6, again, we have this expression which looks quite complicated, but we also do see a function in here, this inside function, and its derivative. And so we're going to key into these grouping symbols here, and we know that when we are identifying an expression to remove, we're typically removing something inside some grouping symbols. So we're going to remove the x cubed. So that's what we're going to remove. Step 2, we're going to set that equal to u. And then step 3, we're going to differentiate this. So we're going to end up with du dx equals 3x squared. Step 4 is solving that for dx. So we're going to multiply both sides by dx. And then we're going to divide each side by 3x squared to solve for dx. Step 4 then is the substitution. So looking at this expression, we have to decide on every component what stays and what goes. So we start with the integration sign, that stays. The x squared, we have nothing to substitute out for an x squared, so we just keep that. The sign stays for the same reasons. The x cubed, we can rename u. So we're going to put in a u there. And then the dx, we're going to pull that out, and we're going to replace it with a du over 3x squared. And so we see that since we have this relationship between this inside function and its derivative, that the derivatives end up canceling out of the expression. And this 3 in the denominator is really a fraction of 1/3, and we're going to pull that out front of the integrand, and so we're going to have 1/3 sine of u du, which is a much simpler expression to take the antiderivative of. So step 6 then is we're going to integrate this. So we have the 1/3, and then the antiderivative of sine of u is minus cosine u. So we're going to simplify that up a little bit, and we're going to do our 7/8 combo. We're going to put the minus out front, so it's going to minus 1/3, and then cosine of u is going to be cosine of x cubed. We're going to do that replacement, plus c for the indefinite integral. Now, before we get to steps 7 and 8, we have to examples 7 and 8, we have to realize that examples of 7 and 8 deal with definite integrals. In other words, if you look at them on your paper, they have an upper and a lower bound. So in this case, we're going to stick with the same A-step strategy, but at the 8th step here, you notice we kind of can do either one or the other. Up until now, we've done this on the 8th step. For these next two examples, we're going to do this. We're going to evaluate the definite integral. And so we're not going to, in order to do that and to do that easily, one way we can accomplish that is that actually when we get the substitution for u there in place, we're never going to go back to x. It's easier to evaluate that way. So let's take a look at this example here. So again, this u sub strategy that we use, we have to look for a function and its derivative, and sometimes they're pretty sneakily hidden. And that gets back into this definition about when we can do a u sub. And remember that we have this nested function, this g of x, and inside also the integrand here we have the derivative of g of x, and so that's that big indicator that we can use the u sub. So here in this one it might be a little harder to see, but we have a function tangent and its derivative secant squared. So that's the function we're going to look to substitute out. So we're going to look to substitute out the tangent, and we're going to go through our 8-step process just like we always have. So we're going to set the expression, that expression tan x equal to u. And step 3 is we're going to differentiate that. So du dx equals secant squared x. Step 4, we're going to solve for dx. So we're going to multiply both sides by dx, and we're going to divide then by secant squared x to get our dx. Step 5, we're going to do what we've always done. We're going to substitute back in to the integral. Now, the one thing is, though, is since we're going to put in expressions and transition over to variable u, we're going to not include these limits of integration. So we're just going to put an integral symbol. And these limits refer to values for x. But since we're leaving x behind and bringing the variable u, the substitution variable, with us, we're going to have to find new limits. So let's go through this piece by piece. The tan x, we don't keep it. We replace it with a u. The secant squared x we keep, and the dx we replace with the du over secant squared x. And so, again, since we have this relationship between function and derivative, we can see that the derivatives cancel. And so we're left with taking the antiderivative of u du. And so, we know that this is obviously much easier to integrate than this. So as we take the antiderivative of this, we bump up the power by 1 and divide by the new power. And notice now that after this, we don't put a plus c in anymore. This is a definite integral, so we need to get a numeric answer. And the way to do that then is we need to evaluate this, but we need to find the new limits. They're no longer 0 and pi over 4. Those are limits for if we had x in the expression, and we don't. We have a u. So we have to go back to our substitution that we did, and that substitution is u equals tan x. From there, we can find new u values. So if we let tan of x, if we let x equal pi over 4, if we look at this upper limit, and we put in pi over 4 here, then u is equal to tangent of pi over 4, which is 1. And then if we take this lower limit and put it here, then u for the lower limit is tan of 0. And so that ends up being, tan of 0 ends up being 0. So our u upper and lower limits are 0 and 1. So we need to evaluate our expression in terms of u between 0 and 1. which means putting in 1 and squaring it and dividing by 2, and then putting in 0, squaring it, dividing by 2, and subtracting it. And so our evaluated definite integral between for this expression here is going to be a half. So if we look at example 8, we're going to run through this again. We can see the relationship here between having a function and its derivative. We're going to go through our 8-step process again. We're going to identify that expression to remove. Step 2, we're going to set that equal to u. Step 3, we're going to differentiate that. So du dx equals 3x squared. Step 4, we're going to solve for dx. So we're going to multiply both sides by dx. And we're going to divide both sides by 3x squared. And then we can go ahead and get our easier integral. And this easier integral is going to be in terms of u, and we're going to have to get our new limits. So we're going to go through piece by piece, and we're going to drop the upper and lower limits until we're done integrating. So we keep the 3x squared. We keep the radical, but we're going to remove this and replace it with u. And we're not going to keep the dx, we're going to replace that with du over 3x squared. And then if we've done this all right, this relationship between function and derivative is that derivative is going to cancel, and we're going to be left with evaluating the square root of u du, which is the same as the u to the 1/2 power. And so as we integrate them, we bump up this power by 1 to get u to the 3/2, and then we divide it by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So here is our integrated expression in terms of u. And so now we're going to come back and use this substitution to find our new upper and lower bounds so that we can evaluate the u expression instead of the x expression. So ignore this. I have this sequencing out of order apparently. So our substitution, if you remember, is u equals x cubed plus 1. So when x is negative, no, I think I do the top one first. When x is 1, then we have 1 cubed, which is 1 plus 1. U should be 2. So when x is 1, then u is 2. When x is negative 1, negative 1 cubed is negative 1 plus 1 is 0. So when x is negative 1, u is 0. So our u limits are from 0 to 2. And if we plug them into our u expression, we get 2/3 2 to the 3/2 minus 2/3 0 to the 3/2. This whole thing is 0. So here's our answer, 2/3 times 2 to the 3/2. Now you're not going to see an answer in terms of a fractional power like this. So let me go through a few equivalent expressions. 2 to the 3/2 is saying 2 cubed to the 1/2 power, which is also saying 2 cubed and square rooting that. So let's deal with this 2 cubed first. 2 cubed is 8. And then we're going to have a square root next to it, or we're going to have it under the square root. So 2 cubed is 8, and then that 1/2 power is the square root. So 2 root 8 over 3, you might see that, but really we're going to simplify this. 8 is 4 times 2, so this is really, we can bring out a 4 as a perfect square of 4 as a 2. So this square root of 8 is really 2 root 2. So bringing in this numerator then is really 2/3 times 2 root 2, which is 4 times the square root of 2 over 3. And this, I think this is how you're really going to see it. So you have to kind of recognize the mathematical equivalence between this and this. That will be helpful in multiple choice questions. Just a last mention about some integration that we can do, what I call on the quick. In other words, do it quickly. And that is when we have linear inner functions. So we know we always talk about these u subs. We're looking for these inside functions that we identify and call u. Well, if we look at these integrals 2, 3, and 4. For instance, here's e to the kx. Now we know if this was just x, that the antiderivative of e to the x is e to the x. But it's a linear multiple of x. So e to the kx would be something like e to the 7x. Okay. And so we could do a u sub here and call u equal to 7x and go through the 8-step process. But really, what happens is that if it's just a linear multiple of x, we end up just doing the antiderivative and then dividing by the derivative of k times x. So let's pretend this was 7. The antiderivative of e to the 7x would be e to the 7x divided by 7. That's integration on the quick. That's kind of sidestepping the 8-step process with these linear factors. So for instance, the antiderivative of e to the 5x, so e to the 5x equals e to the 5x divided by 5 plus c. And we can do this with trig functions and linear factors in here as well. Sine to the 4x minus 1, that's linear. Okay, the antiderivative of sine is negative cosine, so we're going to have negative cosine of 4x minus 1 divided by the derivative of this plus c. So in each case, we're just dividing by the derivative of that linear expression. Derivative of 5x is 5. Derivative of 4x minus 1 is 4. Let's try an example for this last one. The antiderivative of cosine of 1/3 x plus 7. So we're going to say that's sine of 1/3 x plus 7 divided by 1/3. Okay, so it's do the antiderivative of 1/3 x plus 7 divided by the derivative, which is 1/3. Dividing by 1/3 is the same as multiplying by the reciprocal, so that's the same as multiplying by 3. And then putting your plus c. So that's, I call that integration on the quick. It's just it's a side step or a substitute for a long and drawn out u sub. So just to kind of recap how substitution is used to make integration easier, that u sub strategy makes integral expressions simpler to process. So instead of having something long and complicated with lots of powers, that you have something that is a single power that is much easier to integrate. At this point, you should be able to do day 2 of section 6.2, and you should be ready to take the first quiz from this section as well if you want to try to do a proficiency quiz instead of a WebAssign.